This video will discuss creating custom correlations for CoilDesigner software. The sample coil shown here is included with the CoilDesigner software and is a tube-thin R134A 28BY3 evaporator. There are two types of custom correlations that can be uploaded to CoilDesigner. The first is an external correlation, which is implemented in a user-specific library contained in a DLL file. The second is a user polynomial, which allows users to specify a correlation in a power series format. This type of correlation is created within the CoilDesigner software. This video will explain how to create each of these types of correlations. For information on using these correlations within CoilDesigner, please consult the CoilDesigner help file, further tutorial videos, or contact support at optimizedthermalsystems.com. The first type of correlation that we will explain is the user polynomial type. To create this correlation, go to the Tools tab in CoilDesigner and select User Correlation Editor. This will bring you to the Correlation Editor menu. To create your own correlation, press File, then New. This will not really change anything visually about the menu. In the tab on the left, there is a list of all the different correlation types supported by CoilDesigner. Your custom correlation may be applicable to multiple of these types. However, you will need to input the information about the correlation individually in each category in order to be able to apply it to all those categories. To create a correlation, select the type of correlation you would like to create and right-click or control-click. Then press Add. If done correctly, this should produce a small box with a plus in it to the left of your correlation category. Press on the box, then select the new correlation with a number attached to it. This is where you will create your custom correlation. On the top left, there is a box with basic information about your correlation. This includes the title, which you may input, and the correlation format. Every correlation format takes the same form, but underneath that, it clarifies the inputs and outputs for your specific correlation type. On the top right, you may choose between SI units and English units. And below that is a box with input range, which is not currently functional, so no values should be inputted there. On the bottom left is where you actually enter your correlation information. You will enter the coefficients and the exponents for your power loss series correlation. Once you have entered all of the coefficients and exponents, and there is no limit on the number you may enter, press Update Chart. Once you have finished entering the information about any single correlation, press Save This. This allows you to return to the menu on the left and create correlations in different categories. You may create as many correlations in as many different categories as you would like in any one sitting, so long as you remember to press the Save This button in between them. Once you are done creating correlations in all the different categories, go again to File and press Save. Name your correlation and save it. Note that it saves as a CoilDesigner correlation file because it has been created entirely within CoilDesigner. This video will now discuss how to create the external library type of correlation. These correlations are created using Microsoft Visual Studio. So in order to follow along with the video, Microsoft Visual Studio will need to be installed on your device. Once Visual Studio is open, select Create a New Project. The type of project must be a C# class library .NET framework. There are other projects which may have different kinds of .NETs, but it is important to use .NET framework because this is also what is present in the CoilDesigner software. Once you have selected the project type, you can give it a name, a folder location, and a .NET framework. Selecting the framework is extremely important. You must select a framework of at least 4.7 because the current version of CoilDesigner software runs on a .NET framework of 4.7. Anything lower than that will not function on the CoilDesigner software. Once you have made these selections, you are ready to create your project. Microsoft Visual Studio projects have a number of different windows. The largest, entitled Class 1, is where the coding is done. On the bottom is the solution window or the error window. Errors in the code will pop up here as they are identified and then disappear as they are rectified. On the right is the Solution Explorer, where there is information about the properties, references, and the class of the code. The CoilDesigner software comes equipped with a couple of DLL files to assist in creating custom correlations. These files provide a framework for the code, which enables the code to work more smoothly once uploaded to CoilDesigner. To reference these files, you can either go to the References tab in the Solution Explorer window and either right-click or control-click on it and select Add Reference. Another way to add a reference is to go to the Project tab at the top and select Add Reference from there. From there, select the Browse button on the bottom, and within the CoilDesigner folder, select the specific file ceehxtfmc.common. Add this file, make sure that it is checked, and press OK. If you have added the file successfully, when opening the Reference tab, you should see the file name there. Now we are ready to begin actually coding. The first step of coding is generic and applies to any kind of custom correlation that you are coding in Visual Studio. On the public class, Class 1 line, add a colon and begin to type UMD. What we are doing on this line is making sure our code will reference the DLL file that we added to the References tab. We do this so that we can implement its framework and make our work when coding much easier. If you have properly added the file as a reference, as you start to type UMD, Visual Studio should pop up with a little drop-down menu that has UMD CEE there. Throughout this line, you should see this drop-down menu pop up several times to assure you that you are on the right track, and instead of having to type everything individually, you should be able to select from the drop-down menu. Here, we will select the UMD CEE and press Enter. After typing that, add a period, and then another drop-down menu appears. Select what is present here and press Enter again. Then add another period. Now, the drop-down menu has a variety of different options. We are trying to create a custom correlation, so we will want to reference the correlations aspect of the reference file that we added. Start to type correlations, and then once you see in the drop-down menu simply the word correlations with 2 curly brackets pop up, you may select it and press Enter. After that, put one final period and type the letter I. I stands for interface. We will want to choose the first option in the drop-down menu, IHXTFMC correlations. If you mouse over it, you can see that it is an interface for implementing user correlations, which is exactly what we would like to do. Select it, then press Enter. Your typing on this line is now done, but as you can see, a lot of errors have popped up in the error section of the window. All these errors complain that Class 1 has not implemented the interface yet. To rectify these errors, go to the left where there is a little light bulb with an X on it, right next to the line numbers. Press the down arrow and select Implement Interface. Mousing over this reveals a preview of the interface. Press Enter, and now all of your errors should disappear and a whole batch of code should deposit itself into your file. The interface that we have just implemented contains a bunch of different codes that do lots of possible outputs. Some of them are obvious, such as get coil cost, while others have abbreviations, like airside heat transfer coefficient. Your custom correlation may be able to implement the titles of one or more of these coding sections. For every option that your custom correlation applies to, you may delete the default line of code and enter your own code. For this video, I will be demonstrating how to code the Dittus-Boelter correlation. So I will be coding in the Get Airside Heat Transfer Coefficient section. The Dittus-Boelter correlation states that the Nusselt number, using the hydraulic diameter, is equal to 0.023 times the Reynolds number raised to the 0.8 times the Prandtl number raised to the n, where n is equal to 0.4 for heating and 0.3 for cooling. We will assume that we are cooling our fluid, so n is equal to 0.3. The purpose of this function is to ultimately solve for h, the heat transfer coefficient. In order to do that, we first need to solve for the Nusselt number in terms of the Reynolds number and the Prandtl number. So the first step in coding is to define all the different variables that we will need to solve for these dimensionless groups. I'm going to paste some pre-written code here and then explain each step of it. The first section of code is coding simple physical properties. As you can see, each one is declared as a double. A double is a variable type that can hold integers and decimal places. And after each one, the way it works is that we type in air inputs, which is located here at the top of the function. This is because our function here is working on the air side of the heat exchanger. Just like when we were typing in the top line, we get a drop-down menu where we select air inputs, then press enter. Then, adding a dot after air inputs generates another drop-down menu which has functions for all of the basic physical properties that you might need for airside parameters, including average velocity, conductivity, density, and specific heat, all of which are present in our correlation. Right now, we are declaring the variable rho, which I am using as density. So I select air density, then press enter. The most crucial part of the coding is that the end of each line must have a semicolon. This suppresses the code and enables it to run. You can copy the same process for all of the rest of your physical property variables, giving them whatever names you choose. The next section here are the properties that work toward the composite property of the hydraulic diameter. Because a hydraulic diameter is theoretically different for different types of conduits, rather than having its own function, it is made up of other properties. To make the hydraulic diameter, we require the minimum free flow area, the tube width, or airflow length, and the fin area plus the tube area, which is the total heat transfer area. In order to annotate your code, just add these two slashes. Once we have defined these three properties, we can combine them in simple mathematical ways to create the hydraulic diameter, using the star on top of the 8 as the multiplication operator and the / as the division operator. As you can see, each line has a semicolon at the end of it. Now that we have declared all our variables, we are ready to declare our dimensionless groups, just like how we declared the hydraulic diameter. Because our dimensionless groups will be made up of doubles, we must also declare them as doubles. First, we can declare the Reynolds number, which is the density times the average velocity times the hydraulic diameter over the viscosity. Next, we can declare the Prandtl number, which is the viscosity times the specific heat over the conductivity. Now that we have declared those two, we are ready to declare the correlation function itself. As with all the other variables, you can give this function any name. I'm going to call it NU for the Nusselt number because that is what it is technically solving for. Within Visual Studio, there are some existing functions that allow you to do exponents. To access those, type math, or enter it from the drop-down menu, and then a dot. As you can see, a whole drop-down menu list of functions will come. The function for exponents, where you can specify both the value being raised and the power itself, is POW, short for power. As you can see when you mouse over it, you feed this function two doubles, where the first number is the number being raised to a power, and the second number is the exponent itself. You can input this, then inside the parentheses, we will first do the Reynolds number and 0.8, then, following the same process for the Prandtl number and n. We can use n because we have declared it above. This line 2 also requires a semicolon. Now that we have defined the Nusselt number, it is finally time to actually define our heat transfer coefficient. The heat transfer coefficient is equal to the Nusselt number times the conductivity divided by the hydraulic diameter. Now we are at the very end of our code. The last thing we need to do is to tell the code what value we actually wish it to return. To do that, we type return, and then in our case, because we have been solving for the heat transfer coefficient, we type H. Once we have finished this, you should see no errors in the code. Once you have completed your code, you can export it as a DLL file. The way to do this is at the top, you may select either debug or release. Debug will run your code and show any errors on the bottom, while release will not check your code for any errors. After that, select any CPU and press the green arrow to start. This will transform your file. In the output window below, you will see a file path to your file. This is where you will find it if you wish to upload it into CoilDesigner. For more information on uploading your file in CoilDesigner, please contact support@optimizedthermalsystems.com, consult the CoilDesigner help file, or consult other tutorial videos.